Alright, so I really like LEDs, and especially LED 7-segment displays. I think to some extent, the reason I got into electronics is because I like making LEDs blink. So I do mostly digital electronics, and when I am prototyping and testing digital circuits, I often find that it's useful to have a way of visualizing 8 and 16-bit data values, such as values being generated by an output port or values that are on the address bus of an 8-bit CPU. It's useful to be able to see those in real time. So, if you've been watching this channel, you may have noticed me using hex displays, little breadboard attachable PCBs that have either 2 or 4 7-segment displays on them that can display an 8 or 16-bit value in hexadecimal. So here is a recording of me using it to debug the address decoding logic for the 6809 computer system. And I will freely admit, this is not an idea I came up with on my own. It is actually one I stole from Quinn Dunkey. She built a similar 16-bit hex display for her Veronica project. I adapted it to be a little bit more easy to use in a breadboard context. So what we're going to see in this video is some updated designs for these hex displays, and of course the schematics and firmware will be available. Just look in the video description for the link. The main thing I wanted to do in coming up with these new designs is to update the circuit to use slightly more modern 7-segment displays. The ones I had been using are fairly obsolete. The new design uses ones that are a little bit more current. And one of the reasons I think this video might be a little bit interesting is that I will talk a little bit about designing a PCB and also how to solder surface mount components onto a PCB. I don't claim to be an expert at this, but I do have a technique that works for me. Alright, so here is why I have come up with new designs for these hex displays. One of the main reasons is that the original hex displays used these older DIP14 style of hex displays, and they're definitely fine for what they are. I really actually like the orange color of these old displays, but they are definitely kind of obsolete at this point, and they're definitely not very bright, which is a little bit of a problem. So in the new designs, I'm using these, I think, somewhat more modern DIP10 style displays. So yeah, this one here is the HDSP F501. It's definitely a little bit brighter than this guy. But the good news is I was looking on lcst.com, the component distributor, and found some blue LED displays that I believe are compatible with this 10-pin format. So I will definitely try those out when they arrive in a couple weeks, although that's probably not going to be in time for this video. The other problem I wanted to address is that the original 8-bit 2-hex-digit version of the display used an ATtiny 2313 microcontroller, but it used the DIP package version of the microcontroller. So in the new design, it uses an SOIC20 surface mount version, and that will allow the PCB to actually be a little bit smaller in the new version. Before we look at the design, let's talk about how these common anode 7-segment displays that I'm using actually work. So in a 7-segment display, there are essentially 8 LEDs. There are the 7-segment LEDs, A, B, C, D, E, F, and G, and then there is an LED for the decimal point. These are called common anode displays because the anodes of each of the LEDs are connected together. And in the particular displays I'm using, pins 1 and 6 are the common anode pins. In order to light up a segment, or the decimal point, we apply a higher voltage on the common anode pins and then make sure that we have a lower voltage on one of the cathode pins. Each LED has its own cathode pin. So for example, if we want to light up the LED for segment A, we make sure that there is a lower voltage on pin 10, and assuming that we've applied a higher voltage on the common anode pins, current flows from the anode pins through the LED to the LED's cathode pin, and the LED lights up. One problem that we encounter when we attach these 7-segment displays to a microcontroller is that if you attach them in the straightforward way, you will need a lot of output pins. We need one output pin per cathode. And so even if we want to just control 2 of these displays, we will need a total of 14 pins, 7 per display. We're not going to use the decimal points. That means we just need to drive segments A through G on each display, but that's 14 output pins. We still need 8 input pins to actually read the input data values that the hex display is going to display. So 14 plus 8 is 22. That's definitely more pins than our 20-pin ATtiny 2313 even has. So how do we solve that problem? The solution is multiplexing. So what we are going to do is we will only have one display actually lit up at any given time. That means that we will selectively apply a positive voltage to the common anode of one display at a time, and that means that all of the cathodes can be connected to a single set of pins. For example, we can have a single output on the microcontroller connected to pin 10 of every display, and that means we can light up segment A on any display, whichever display currently has its common anode driven to a high voltage. And so what that means is that we just need 7 output pins for the cathodes, and then 1 output pin per anode, 1 for each display. To confirm that we can make this display work using an ATtiny 2313 as the microcontroller, let's think about the I/O pins that we need. We need 7 output pins connected to the cathodes of the segments. We need 2 output pins. Those will go to the common anode of each display so that we can turn each display on individually. And then we need the 8 input pins that will read the data value that the hex display is displaying. That means we need a total of 17 I/O pins. And the good news is the ATtiny 2313 has 18 I/O pins, so this is going to work. One last problem to think about is how much current are we going to need at this common anode pin? And a good estimate would be to assume that each of these LED segments will require 10 milliamps. That's pretty typical. So if they're all on at the same time, that's 70 milliamps of current that need to flow into this common anode pin. The problem is our microcontroller, the ATtiny 2313, is only capable of supplying 40 milliamps. So what we are going to do is we are going to use a PNP transistor to supply current from the positive supply rail into the common anode, and we can switch that transistor on and off using an output pin of the microcontroller, and we will see that when we look at the schematic. Alright, so here is our schematic for the 8-bit version of the hex display, and I think the most interesting thing here is these 2 PNP transistors that are providing the current to the common anodes of the hex display. And so the way these PNP transistors work is that the emitter of the transistor is connected to the positive supply rail. And the way that these transistors work is that if a small current is flowing through the transistor and out the base, and that will flow into the output pin that is controlling the transistor, and so when we produce a low voltage on this output pin, that causes the current to flow from the emitter into the base and into this output pin. When that base current is flowing, a larger current can flow through the transistor and out the collector into the common anode of the LED display that transistor controls. So because we have these 2 transistors, we can independently switch on the positive voltage on the common anode of each of these 2 7-segment displays. There are 2 other parts of the schematic that are worth mentioning. The pins of port D on the microcontroller are used to control the cathodes of the segment displays. So when we drive these pins low, that allows current to flow into the pin, lighting up the corresponding LED of the display that is being driven. We use some resistors to limit the current through the LED. Port B is used to read the 8 bits of the data value that we want to display in hexadecimal on the hex displays. These pins will be connected to whatever portion of the circuit we want to display data from. This could be the output of an output port, it could be data on an 8-bit bus, and so forth. The PCB will have a 6-pin header that connects to the programming pins on the microcontroller, and this will allow us to download the firmware program onto the microcontroller once it is installed on the PCB. 2 pins on the PCB will connect to the power supply rails on the breadboard, and this is how the hex display will be powered. All right, let's take a quick look at the firmware program. So here is the main function of the firmware program. We set port B to be an input. we enable pull-up resistors on each of the 8 input pins on port B, and that means that the input works correctly even if there is not a signal actively being driven on the input. We set ports D and A to be outputs, so port D is the outputs to the segment cathodes. We use the low 2 pins of port A to control the 2 common anodes for the 2 LED displays. In the main loop of the program, we call the update display function and then delay for 8 milliseconds. So that means the update display function is going to be called about 125 times per second. The update display function uses a global counter, and this is what allows us to alternate between the 2 LED displays. So depending on which one should be activated next, we read data from port B, select either the high 4 bits or the low 4 bits, enable the correct output pin on port A in order to turn on the common anode of the display that we want to control, and then we output onto port B, which controls the segment cathode, a font value corresponding to the 4-bit integer value that was read. There are 16 entries in this G_hex font array. Each one corresponds to the correct pattern of segments for one of the 16 hex digits. The G_hex font array simply consists of 16 entries that describe the pattern of segments that we want to be activated for each hex digit. Note that we invert these values because in order to activate a segment, we need to drive its cathode low, meaning we need to output a 0 on the corresponding output pin. All right, so here's our test circuit. Here's the microcontroller. Here are the 2 transistors that drive the common anodes. These are the 2 7-segment displays. The input pins of port B are currently controlled by this 8-position dip switch, so that when we flip these switches, it will connect the corresponding input pin to ground. Normally it will be pulled up by the internal pull-up on the microcontroller, but when we hit the switch, it will bring it down to ground. And that's how we will test to see whether the correct values are being output on these 2 hex displays. All right, I have my AVR programmer hooked up to the programming pins on the microcontroller, so I'm just going to go into my firmware directory and type make program and then hit enter. And let's see if that works. All right, looks good. Okay, good. Here are the 2 hex displays. They're each displaying F right now because that is the pattern that we get if all bits are high for that particular digit. Interestingly, you can see this sort of cycling pattern on the hex displays here. You don't actually see that in person. That's just an artifact of the frame rate of the camera. All right, let's try to manipulate the dip switches and make sure that we are seeing the correct digits on the display. All right, so here's the test we're going to do. I'm going to drive each of the bits in each hex digit low one at a time from most significant to least significant. Normally, the pins of port B are pulled up by the internal pull-up resistor. As I engage the switch, that will pull the corresponding bit down to ground, and so the values that I should see on the hex digits are 7, then B, then D, then E. I'm just going to try this, and then I will look at the video after the fact. You'll get to see me doing it in real time. Due to the positioning of my hand, I can't see the displays very well while I'm doing this. All right, so let's try this one, let's try this one, and so forth. So these are the 4 bits of the most significant hex digit. All right, let's try the 4 bits of the least significant hex digit, one at a time. And hopefully we're seeing the correct pattern of hex digits on the display. All right, I'm going to go look at the video and make sure that that worked. All right, as you saw, everything worked perfectly, so I think we can declare this circuit as being reasonable. All right, let's talk about how we're going to turn this into a PCB design. Now that we've shown that the breadboard version of the circuit works and we've also debugged the firmware, now we're ready to move on to the PCB design. And in KiCad, there's basically 2 things that we need to do. We need to annotate the schematic symbol, so that means that every component now has a unique designator. So our microcontroller, for example, here is U1. And then we need to choose a footprint for every component in the design. The microcontroller has an SOIC20 footprint. The resistors are going to have a 0805 footprint, this capacitor 1206. So this will depend on which exact parts you're planning on ordering. Once you have those done, you can generate a netlist, and that essentially communicates to the PCB layout software which components and which footprints you have chosen so that you can incorporate them into the PCB design. Alright, so here's our PCB design. It's a 2-layer board, so we can route traces on both the top of the board and the bottom of the board. The place that I start when I work on a PCB is I look at the PCB fabricator's recommended design rules with respect to things like trace widths and via sizes. If I follow the design rules, then I know that the design that I come up with is going to be capable of being manufactured. The next step is to lay out the components. There was essentially only one critical layout constraint in this design, which is that the pins that are going to allow the input from the breadboard needed to be a precise distance from the pins that connect to the power rail on the breadboard so that the PCB, when it's assembled, will fit correctly into the breadboard. Aside from that one constraint, this was pretty much just a matter of placing the components, routing the connections between them. Once I was satisfied with the design, I generated the Gerber files that you then upload to the PCB fabricator, and at that point, you just wait for the PCBs to arrive. All right, here is our manufactured PCB. I went for the black solder mask. I just thought it would look cool, and I think it does. So I'm going to start putting components on here. I'm going to start with this capacitor, and basically the technique is I will dab some flux on a pad, put some solder on it, then using the tweezers I'll maneuver the capacitor into place, heat up the solder, and try to get it held in place on one pad, soldered to one pad. At that point it should be easy to solder the other pad. Okay, let's see how it goes. Alright, with the first pad in place, I think I will now try to solder onto the other pad and basically get it connected on both sides. Let's see if I can get that done okay. Alright, I think we did an okay job on that capacitor. Let's now move on to one of these resistors. Alright, at this point I am ready to try to solder the microcontroller onto its footprint, and basically all you really need to do is get just enough solder onto the pad to make a bond between the pad and the leg of the IC. So let's see if I can just get a little bit of melted solder onto there. Sometimes it just doesn't want to flow. Okay, that's a little more than we needed, but I think that's okay. Alright, let me see what I can do to solder the rest of the pins. Alright, at this point I've got all of the individual component legs soldered to the board. I think my next step is going to be looking at each pair of pins and testing them with the continuity mode of the multimeter to make sure I haven't accidentally bridged any of the connections. I don't think I have, but definitely doesn't hurt to check. Alright, so I checked all of the adjacent pins using the continuity mode on the multimeter, and I did not find any shorts, so that's good. I think what I will do now is, off camera, I will solder the rest of the surface mount components onto the PCB, and I will meet you back when I'm ready to do the through-hole connectors and the LED displays. Okay, I have the rest of the surface mount components on here. These are the current limiting resistors for the LED segments. These are the two transistors that drive the common anodes. So at this point, I just have to solder the pin connectors and the LED displays. Now that all the surface mount parts are on the breadboard, we're ready to solder the pin headers. And I find that when I'm soldering a board that is going to be plugged into a breadboard, it makes sense to actually put the pins in the breadboard, and that way I know that they align properly when I solder them to the PCB. Alright, so let's try to solder these pins. Here we go. Alright, so I think this is quite good. It's in there nice and firmly. I think if we look at the pins, they seem to be pretty well aligned. Alright, so now we need to do the AVR programming header, and we also need to do the LED displays. Alright, once again I'm using the breadboard just to help me keep the pins aligned while I solder, so let's see if I can get these soldered on here. Alright, so I've cleaned up the board a little bit using isopropyl alcohol. I've put the display modules on. Hopefully they're oriented the right way. I guess we'll find out. Now all I have to do is solder them in. Alright, so here we are for the moment of truth. I have the AVR programmer hooked up to the programming header, and I'm going to type make program in the firmware program. Alright, let's see if this works. Alright, so it kind of doesn't work. It looks like quite a few of the segments are not lit up, so I am thinking that there may be some continuity issues either with the microcontroller or the current limiting resistors, or potentially the this anode transistor might not be fully connected yet. All right, time for some debugging. All right, I found one bad solder joint on pin 8 here, which was driving this segment of the LED display, so that does seem to be working now. Now I just need to figure out why this display is not turning on. All right, so I touched up the solder joints on this transistor, and now both segments work. So now I'm just going to touch all the inputs to ground just so I can see what happens when I put a low voltage on the input. And we do see the right patterns, but they're happening on the wrong digits. So what that means is that I have reversed the pins that drive the displays either in the schematic or the firmware program. But the good news is it's extremely easy to change the firmware program. So I think I will do that. I think I will also try to increase the refresh rate and maybe see if I can eliminate some of this flickering. All right, so I looked at the PCB design, and what happened is I just put these in the wrong order on the PCB, so that's really not a big deal. I've corrected it on the schematic and also in the firmware program. I also doubled the refresh rate in the firmware, so now the image appears steady even on the camera. It didn't flicker if you actually looked at it in reality, but you did see the flicker on the camera, so that's been fixed. And now also the input pins now correspond to the correct digit. So, right, and so the least significant input pins now correspond to the least significant digit. So yeah, this is now completely working. All right, so now that we have the 8-bit hex display working, let's try to get the 16-bit hex display working. So there's nothing fundamentally different about it. It has a different microcontroller with more pins in a TQFP package. That's a little bit harder to solder, but not really. It shouldn't be too bad. So I am going to try to assemble this off camera, and we'll see if we can get this one working. All right, here's the assembled 16-bit hex display. I think everything's soldered correctly, so I'm going to once again try make program and see what happens. Okay, actually this is pretty good. We've got 3 out of the 4 digits working. I'm guessing I need to take a look at this transistor and maybe resolder a connection. All right, let me try that. All right, so the problem did turn out to be a bad solder joint on this transistor. So now all of the segment displays are working, and all of the input pins also do work. They all control the corresponding digit just fine, so that's great. The only issue here is that these displays are just not very bright. You can tell if I turn the overhead lights off, it looks reasonably okay, but in brighter lighting, there's just not a lot of contrast between the segments that are on and the face of the display. So I think the problem is that my current limiting resistors that I have installed here are 220 ohms. I think that's just a little bit too high, given that with 4 displays, each one is only on 1/4 of the time. So when my lcsc.com order arrives, I will be getting some lower value resistors, but I will also be getting some blue LED displays that should be much brighter. So when that happens, I will do a follow-up video to make a proper final bright version of these hex displays. But the good news is the circuits work, the PCBs work. I've proved that I can solder these. So overall, I would say this was a successful project. All right, so in conclusion, the new circuit designs work, the new PCB designs work, the new firmware works. The only issue we have is that our displays are not bright enough, but we will fix that in the next video when the new resistors and blue LED displays arrive. So in the meantime, if you are interested in building these designs on your own, the schematics and PCBs and firmware and bill of materials are linked in the video description. All right, I will see you in the next video.